Sheet number 3, questions 1 to 3 for homework. We're going to go over question number 3 right now, and then after that we'll do another example from our example booklet that we got on the first day of class. Number 3 says a 5.00 kilogram ball hits a 75 kilogram man standing at rest on ice. The man catches the ball. How fast does the ball need to be moving in order to send the man off at a speed of 3 meters per second? So picture this, right? Don't just try to do the problem. Picture it, visualize it, see it. See the man being hit by the ball. He catches the ball. Right? I'm standing here, I catch the ball. I go backwards with the ball, right? Do I go faster than the ball was moving or slower than the ball was moving? Slower, right? You can see that. Even if you haven't had formal physics training, you know intuitively that the man and the ball together are going to be going slower than the man with the ball. Now, let's explain that using physics, now that we know a little bit of physics. Why would the man and the ball combination be moving slower than the ball? Yep. Was your hand up? No? Because what? Because he's heavier? Okay. So let's go with that. You're right. You just need a little bit more there. Yep. Okay. So what do we know about the ball before it collides with the man and the ball/man combination after the ball collides? What do we know about those two different places? Yep. Same what? Same impulse, yeah. Well, kind of. The ball will experience an impulse. The man will experience an equal and opposite impulse. You're on the right track here. Yep. Yes. The initial momentum of the ball will be the same as the final momentum of the ball/man, right? So if that momentum is the same and the mass of the man/ball is bigger, well, then the velocity must be smaller, right? If the mass is quite a bit bigger, so the velocity we should expect to be quite a bit smaller. All right, let's label this as object number 1 and this one as object number 2 and write down some givens here. I'm going to say mass 1 is 5 kilograms, and I'm going to say mass 2 is 75.0 kilograms. What else do we have here? What does this rest on ice? That's a velocity, isn't it? What is that, V1 or V2? Is that the velocity of the ball or the man at rest on ice? What is it? It's the man. So that's going to be V2, isn't it? Is that going to be V2I or V2F? That's V2I, the initial velocity of the man before the collision takes place. How fast does the ball need to be moving in order to send the man off at a speed of 3? That's going to be VF, right? I'm not going to call it V2F because it's really the man and the ball, right? Let's call it VF. Some people might like to call it V12 to remind them that it's both, but I usually just call it VF. And we're looking for what? What velocity are we looking for? V1 or V2? V1, yeah. V1I or V1F? Yeah, it's V1I, good. V1I. All right, so let's say PI is equal to PF. Now, we're choosing to analyze the system. And if we analyze the system, then we have to use every mass within the system, right? And we say the total momentum equals total initial equals the total final momentum. We could analyze one object or the other, but if we were doing that, there would be a change in momentum. Each of them experience a change. In other words, if we were analyzing individual objects, we'd have to do impulse. We're not. We're analyzing the system, so we say the total momentum initial equals the total momentum final. Now, how many objects do we have? How many objects do we have, Amelia, before this collision takes place? 2. So we're going to have 2 terms then, M1, V1, I. That's the momentum of the man, of the ball before the collision, plus M2, V2, I. That's the momentum of the man before the collision, right? Colton, how many objects do we have after the collision takes place? 1. Right. It's the man/ball combination. Some of you say, well, the ball's not really a part of the man. You know what? Neither are his socks a part of the man. But we consider that, right? We're saying the man's mass is 75 kilograms. Like, we're counting the mass of his socks and everything else that he's wearing. Hopefully it's not just socks that he's wearing, but whatever he's wearing, right? That's just included in the 75. Well, if we can include the mass of his shirt and his socks, well, why wouldn't we include a mass of a ball that he's holding on to, right? So the total mass is the man-ball combination. One object, man-ball combination. M times V, right? Two objects become one. All right, let's sub some numbers in. M1 is 5.00 kilograms. V1I is, that's what we're looking for. M2 is, what, 75 kilograms? What's V2I? 0. What's 75, Amy, times 0? Yeah, we could have just crossed that off, or even not even included it if we had wanted to, really. I'm just going to include this so we can explicitly draw attention to the fact that it has 0 units of momentum. Total mass is, what, 80 kilograms times VF. Now what we're going to do is just, we know what VF is. That's 3.00. So we're going to say, 240 on this side is equal to 5 times V1I. V1I is 240 divided by 5, which is 48. Is that right? Is that a reasonable answer? We went from 48 down to 3 meters per second? Yeah, our velocity decreased a lot. Why? Because our mass increased a lot. Same momentum, velocity goes down by a ton, well then it must be because the mass went up by a ton. Got it? Yeah? All right, let's take a look at an example here. Example number 2, this is going to be. Some of you may have watched the podcast on this already. If you have, just bear with me again. We'll go through it again here. Most of you probably have not. This is almost the same concept, completely the same concept, but just a couple little subtle differences that you got to pay attention to and watch out for that make this one a little bit harder. Not much, but a little bit harder than those first 3 questions you did on the worksheet. So there's a 0.0060 kilogram ball moving at 3 to the north, collides with another one, same mass, traveling to the south at 2 meters per second. I'm going to draw attention to this. How come? What's the big deal with that? Evan, what's the big deal with that? Yep. So what do we got to make sure that we do since it's going the opposite direction? Finn, what do we got to make sure we do here? Yes. Doesn't really matter which one you make negative, although usually we make north positive and south negative. But it doesn't really matter. You could choose to go the other way around if you really wanted to. First ball moves off at 1 to the south. Immediately after the collision, what's the velocity of the second car immediately after the collision? We're going to call this one number 1, and we're going to call this one number 2, the second one. I'm going to say M1 is 0.060 kilograms. Sorry, 0.0060. Oh man, number 2 is the same thing. That's actually going to be a big help for me. Or not a huge help, I guess, but it's going to be a bit of a help. You're going to see in a moment why this number is a help to me. What do we got here? 3 meters per second. What is that? Is that V1 or V2? Parker? What is it? V1. Um, 2 meters per second to the south. I'm going to make that negative. I'm not going to forget to make that negative because I circled north and south, right? Draw attention to it. Listen, you draw attention to north and south, you might forget to make something negative, but man, are you ever less likely to forget that, right? When you are very, very conscious and explicitly identify little things like that, you are much more likely to do it correctly when you're solving the question. What is that? Is that V1 or V2? At 2 meters per second to the south. V1 or V2? Kaylin, V1 or V2? It's 2 meters per second here. Oh, yes. It's V2. Is it V2I or V2F? Yeah, it's the initial velocity of the second car. What do we got here? The first ball moves off at 1.0 to the south, so something's going to be negative 1.0 meters per second. What is that? Is that V1 or V2? It's V1, yeah. And is that V1I or V1F? The velocity, the first ball moves off after the collision. That's going to be V1F, right? V1F. Notice it says immediately after the collision, isolated system, right? Before any external forces have a chance to do anything. That's what we did in our lab yesterday, right? Just before and just after, so that we can minimize the external forces. We're looking for the velocity of the second car immediately after. We're looking for V2F. Now, man, there's a lot of stuff going on here. But you know, like as much as there's a lot of variables here, it's not really that bad if you're conscious of what you're doing here. We're going to say, because we're analyzing the system, Pi equals Pf. There are two objects before the collision, M1 V1I, M2 V2I. Object number 1, object number 2. How many objects do we have? How many objects, Paige, do we have after the collision? Still 2. So instead of calling it M total times Vf, we're going to call it M1 V1F plus M2 V2F. Good. The only difference so far is the structure of the equation, right? We don't think anything differently about this question than we thought about that worksheet question number 3 that we did. We think about it exactly the same way. We ask ourselves, how many objects do we have? Just the answer to that question is different here. After the collision, in that question number 3, there was 1 object. This time there's 2. We got an MV term for every object. Now here's where there's a bit of a shortcut. This doesn't always work out, but it does in this particular question. Anybody want to identify what it is?
Yeah, the same mass.
Yes, if it has the same mass, even though they're different objects, the same mass ends up canceling, right? Now, I'm going to cancel those, but know that that doesn't usually happen. It has to be the same value in every term. V1I is 3.0, V2I is negative 2.0, V1F is negative 1.0, plus V2F. 3 plus negative 2 is 1. Take the 1 over by adding, and I get 2.0 meters per second. You can imagine maybe if you're a police officer who's in charge of investigating accident scenes, how something like this might be really, really useful. Except you're not likely going to calculate the velocity of a car after the collision. You're likely to calculate the velocity of a car before the collision, right? Was the driver of this car speeding before he hit or before she hit this other car? So instead of solving for V2F, maybe you solve for V1F. V2I or V1I. Does that make sense? Going to have you, if you haven't done this already, if you haven't got these done, have a peek right now at worksheet number 3. That's the one that you were working on yesterday, and do questions 4 and 5 right now. Worksheet number 3, questions 4 and 5. Give you a few minutes to do that, and if we can, we'll try one more example in class here today. Yeah, let's do that. In 10 minutes, at 1:46, we'll take a look at one more example, and I'll leave you with a couple questions for homework. Let's do one more example. This is number 3. Everybody's going to focus here away from your questions that you were working on and now up on this. This one says a 75-kilogram man stands on ice while holding a 2.5-kilogram ball, throws the ball forward. What's the velocity of the man immediately after he throws the ball? Listen, I'm standing on ice. I throw a ball forward. No friction on the ice, or at least very little friction on the ice, right? So as I apply a force on the ball applies an equal and opposite force on me. If the ball experiences a positive impulse forward, then I experience a equal and opposite negative impulse, or in other words, backwards. In other words, if the ball goes forward, I'm going to go backward, right? Now, would you expect me, the 75-kilogram man, to move faster or slower than the ball? Ball moves forward at 15. Am I going to move forward at faster than 15 or slower than 15, Chloe? Slower than 15, right? Same amount of momentum, right? Momentum has to be conserved, same amount of momentum, but I'm much heavier than the ball is, so I should be going much slower than the ball is. All right, let's call this number 1, and let's call this one number 2. I'm going to say M1 is 75.0 kilograms. I'm going to say M2 is 2.5 kilograms. What else we got? 15 meters per second? Is that V1 or V2? The man throws the ball forward at 15. So that's V2. Yes, that's the velocity of the ball. Is that V2I, Sam, or V2F? Yes, that's the velocity of the ball after it's thrown. Good. We want to find the velocity of the man after he throws the ball. That would be V1F. Is there anything else that we have here if we read between the lines? Yep. So the initial, let's just call it VI, since they both start at 0, and really it's one object before, right? The man-ball combination, like the man-sock combination, one object, one mass, 75 kilograms. 0 meters per second. Good. Now let's say PI is equal to PF. We could analyze the impulse experienced by the ball or the impulse experienced by the man. But if we're analyzing both the ball and the man, then we have to do conservation of momentum. How many objects beforehand? Colleen, how many objects do we have before the man throws the ball? Just one. What's its momentum? Some of you might write in M total times VI. You can do that. But what's VI? 0. So the total momentum initial is 0. What's the total final momentum? 0. But let's break it up into M1 V1F plus M2 V2F, because we do have two objects that make up that 0 momentum. M1 is 75. V1F is what we're looking for, plus 2.5 times V2F, which is 15. Let's say 2.5 times 15 gives me 37.5. Let's take that over to the other side by subtracting. I get negative 37.5 on the left side. And now let's divide that by 75. Gives me a value of negative 0.5. It should be negative, shouldn't it? The ball went forward. I should go backward. The ball went forward with 15. I went backward with 0.5. Should it be that much less? Yeah. Why is it that much less than the velocity of the ball? Because my mass is that much more than the mass of the ball. Does that make sense? If your velocity, if your mass goes up by a factor of whatever, then your velocity has to go down by the same factor of whatever. All right, I want you to finish for homework tonight, please. 4 and 5 that you were working on, but also number 6. If you're not done, or if you don't get number 7, that's okay. That's a pretty big challenge question, actually. If you want to take a look at number 7, feel free to do that, but it's not formal homework for you. So worksheet number 4, it is. No, worksheet number 3. Number 4, 5, and 6.